So today we're going to start a new chapter, and of course a new topic with it. Chapter 10 is called Parametric Equations and Polar Coordinates. So the idea of this chapter is that we're going to try to extend calculus, namely tangent lines and areas, derivatives and integrals, to curves that are not necessarily defined by functions. So in 10.1, we're starting with curves defined by parametric equations. So the idea here is, prior to this class, in all of your previous experiences in math, whenever you needed to come up with some kind of curve, you'd usually take the graph of a function, or there are a few curves that you know that are not functions, like circles, for example, and you just say the curve is the set of points that satisfy that equation. For example, if you had something like y equals x squared minus 1, well, the graph of this is a certain curve. Specifically, it's the set of x and y such that y happens to be x squared minus 1. Okay? The notation here just means, these braces just mean set of, and this bar just means such that. So the set of xy such that y equals x squared minus 1. If a point xy satisfies this condition, that its y coordinate is its x coordinate squared minus 1, then it's on this curve. Okay? So prior to this class, this is how you defined pretty much all curves, just by these equations that relate x and y. Okay. Now, there is another way to describe a curve in the Cartesian coordinate plane, and that's using what are called parametric equations. The idea here is, rather than having x and y depend on each other, you can have x and y depend on a third variable, which you call t. Okay? Or usually called t. So let me explain how this is done with an example. So describe the curve given by the parametric equations x of t equals 4 sine t, y of t equals 5 cosine t, for t between 0 and 2 pi. Okay? So here's how it works. First of all, rather than saying x is the independent variable and y is the dependent variable, in this situation we're saying x and y are both dependent on an independent variable that we're calling t. Okay? T is not going to be part of our graph, it's just going to be a number that's going to increase from 0 to 2 pi. Okay? And the idea is, we're going to trace out a path so that the x coordinates always satisfy this equation and the y coordinates always satisfy this equation. Okay? So here's how it works. So when t equals 0, x is going to be 4 times the sine of 0, and y is going to be 5 times the cosine of 0. Well, it just so happens that the sine of 0 is 0 and the cosine of 0 is 1, so that means that we're going to be starting when t equals 0 at the point 0, 5. So 1, 2, 3, 4, 5. So starting at that point right there, 0, 5. Now, when t increases from there, x is going to increase because sine increases close to 0. So x is going to become positive. Y is going to become, well, still positive, but less so. Eventually, when t gets to pi over 2, we're going to have 4 and 0. So that's going to give us the point 4, 0. And so what's happening is this curve is going from here all the way down to here. Then, as t increases from pi over 2 to pi, well, when t equals pi, x is going to be 0. Y is going to be negative 5. So we get the point 0, negative 5. And it just comes down like this. It's not a perfect diagram, just so you know. I'm not very good at these. And then when x is 3 pi over 2, or sorry, when t is 3 pi over 2, then x is going to be 4 times the sine of 3 pi over 2, that's negative 4. And y is going to be 5 times the cosine of 3 pi over 2, which is 0. So we'll get the point negative 4, 0. And then as t goes between 3 pi over 2 and 2 pi, it's going to come all the way back up to 0, 5. So we get, first of all, this curve. We also get a notion that it has a kind of direction to it, right? Because as t increases, the curve is being traversed this way. And so that is what this curve would look like. All right? Now, this, by the way, can be written in a Cartesian way because sine and cosine have a relationship that we can write them in terms of each other without using t. So we can say x over 4, well, that's sine t, and y over 4, or no, y over 5, that would be cosine t. Now, sine squared plus cosine squared happens to always be 1. So since sine squared t plus cosine squared t is equal to 1, that means that x over 4 squared plus y over 5 squared is equal to 1. Okay? And this is the curve x squared over 16 plus y squared over 25 equals 1. You might have learned in pre-calculus that this is the equation of an ellipse. Specifically, it's the ellipse whose x-intercepts are 4 and negative 4, and its y-intercepts are 5 and negative 5. Okay? So these are just two different descriptions of the same curve. This one just describes it by an equation that relates x and y. This one describes it by the path of a particle as t increases. All right? All right, so then let's do another example, of course. So let's say x of t equals x of t equals 1 minus t, and y of t equals the square root of t. And in this case, I'm going to say t just has to be greater than or equal to 0. Okay? So the idea is, I should have probably said this before, but the idea is this. All we need to describe a curve is a relation that gives x in terms of t, a relation that gives y in terms of t. These are called the parametric equations. And then a range over which t can vary. All right? Now in this case, let's take a look at this for a second. You can rewrite this first equation as t equals 1 minus x, right? Okay, now y is the square root of t, so that means that y is the square root of 1 minus x. And so that is a Cartesian description of the same curve. Wait a second. Huh. I appear to have made a mistake in my notes. So then does this, yes, this is affected. Okay, I'll just have to fix that up by the time I post this lecture. Okay, so this is a certain half of a parabola. Okay. Specifically, this is a piece of the parabola y squared equals 1 minus x, which is the same as x equals 1 minus y squared. And specifically, it's just the part where y is non-negative. So when t equals 0, x is going to be 1, y is going to be 0. So we just have this point right here. And then when t is 1, x is going to be 0, y is going to be 1. When t is equal to negative 1, x is going to be, wait, no, when t is 1 is 2, x is going to be negative 1, and then y is going to be the square root of 2, whatever that is. So that might be approximately like right there. And then it's just going to do the normal parabola thing, according to this equation. Okay. By the way, as t increases, x is decreasing, so that means the curve is going leftward. Now, this next example is different in the sense that it's a bit more theoretical. So the parametric description of a curve, okay, that's an alternative way to describe a curve from the Cartesian description, but can it do everything that a Cartesian description can do? The answer is yes, okay? So, for example, if y equals some function of x, well, that's some curve. It's going to be the graph of some function in the xy plane, right? Then the graph of f can be described by x of t equals t and y of t equals f of t. Regardless of what f is, this will always be a parametric description of your graph. Because after all, the graph is literally just the set of points x, y, such that the y-coordinate is f of the first coordinate. And no matter what t is, this would satisfy that. For example, so sub-example, if y equals f of x is like cosine of x, this can be described as x of t equals t, y of t equals cosine t. Same curve, just a parametric description rather than a Cartesian one. Okay? So in other words, the parametric description can do everything that a Cartesian description can do, and it can also do more. Let's look at another example. So let's say this one is x equals 5t plus 3, y equals 5t plus 4, and we're talking about all real values of t. What does this curve look like? Well, you just take a look at this for a second and you realize if I take x minus 3, then that's 5t. And if I take y minus 4, that's also 5t. So then a Cartesian description of this curve would be x minus 3 equals y minus 4. In other words, y equals x plus 1. So this is a certain line. It's just the line with a slope of 1, y-intercept of 1. So looks something like this, right? And by the way, unlike the Cartesian description, this parametric description does have a direction to it. As t increases, x and y are both increasing. So as t increases, the curve is being traversed this way. All right, then let's look at the following. Suppose instead we were dealing with the parametric description 3 minus 1/3 t and 4 minus 1/3 t. Okay, well, you look at this for a second and then you realize if you want to relate x to y to get a Cartesian description, you just have to do pretty much the same thing as the last time. You just need to say that x minus 3, well, that would be negative 1/3 t. And it so happens that negative 1/3 t is also y minus 4. So x minus 3 equals y minus 4, which means that y equals x plus 1, and then this is the exact same line. Okay? So this example illustrates that there's certainly more than one set of parametric equations that can describe the same curve. Okay? Because this example and the last example both look like that, with the same orientation and everything. Oh, actually, now that I think about it, as t increases, x is decreasing, and y is also decreasing. So actually the orientation is reversed. It's the same shape, same curve, but actually it's going this way. This is an example of how the Cartesian description when you convert from a parametric description to a Cartesian description, you lose information, because the Cartesian description just says it's this line. It doesn't tell you anything about the orientation. Whereas the parametric description tells you, well, t is increasing, so as t increases, x and y are decreasing, so it's going down this way. Okay, let's look at another one. So let's say x of t is 3 plus 2 cosine t, and y of t is 2 sine t. And let's say t is not going between all real values. Let's just say t is bounded between 0 and pi over 2. Okay. Well, again, if you want to come up with a Cartesian description for this, which, by the way, is a good idea because we're more used to Cartesian descriptions than parametric ones. If you want to come up with a Cartesian description for this, then we have to relate cosine and sine somehow. Easiest way to do that is with the Pythagorean identity, which just says cosine squared plus sine squared is always 1. So, all we need to do here is say x minus 3 is 2 cosine t, y is 2 sine t. Now, suppose we were to square both sides of both of these equations and then add them together. So we'd be looking at x minus 3 squared plus y squared is equal to 2 cosine t squared plus 2 sine t squared. This is 4 cosine squared t plus 4 sine squared t. Then you can factor a 4 out of those two terms. So you get 4 times cosine squared t plus sine squared t. Cosine squared t plus sine squared t is always just 1. So then this is just 4. So we have x minus 3 squared plus y squared equals 4. Now, hopefully at some point in pre-calculus, you learned that this happens to be the equation of a circle. A circle centered at the point 3, 0 with a radius of 2. Okay. So let's see here. Let's go out by 3 on the x-axis. Actually, we're going to need 5 units on the x-axis. Okay, and then 2 units up and down the y-axis. So then 1 and 2, 1 and 2. Okay, center is at 3, 0. So 3, 0 is this point right here. And then it has a radius of 2. So that means that it's going to pass through this point, and also this point, and this point, and it'll be a circle. So something like this. Okay. But that's not it, is it? Yes, this is x minus 3 squared plus y squared equals 4, but the Cartesian description has less information than the parametric description, because the parametric description says that t has to go between 0 and pi over 2. Now, if t is bounded between 0 and pi over 2, that means that cosine t is at most 1 and at least 0. Okay. If cosine t is at most 1 and at least 0, then that means that x is at most 5 and at least 1. No, at most 5 and at least 3. Okay, so that means that we definitely should not have any part of this circle that has x being less than 3. So let's just erase that part. Additionally, when t is between 0 and pi over 2, sine is between 0 and 1, which means that we should not have any negative values for y. So in fact, all we get is just that part of the circle. And by the way, as t increases, x decreases and y increases, so we get a counterclockwise motion. All right? And so this illustrates, again, that the Cartesian description has less information than the parametric description, because the Cartesian description would give you the whole circle, whereas this is specifying, no, I just want part. Okay? All right, let's look at another one. X of t equals sine t. Y of t equals 1 minus cosine t. T is bounded between 0 and 2 pi. So again, we just need to come up with a Cartesian description for this, and then hopefully that will give us some information about what this curve looks like. All right. Well, again, it has sine and cosine with the same argument in it. So let's see if we can just use the Pythagorean identity. Okay. So let's see here. X of t is sine t. Y of t is, or well, it is, but I wanted to say here cosine t is y minus 1. 1 minus y, actually. 1 minus y of t. Okay? Now again, square both sides and add them together. You get x squared plus 1 minus y squared equals 1, because cosine squared plus sine squared is always 1. All right. And then this is, well, you might not see it immediately, but this is a circle. This is a circle because 1 minus y squared is the same as y minus 1 squared. So actually, what's going on here is we have x squared plus y minus 1 squared equals 1. And then that describes a circle of radius 1 centered at the point 0, 1. So something like this, except better and not drawn by hand. And by the way, when t is 0, x is going to be 0 and y is going to be also 0. So it's going to start at the origin right here. As t increases, sine is going to increase, and so x is going to increase. And 1 minus cosine is also going to increase. So we get a motion that goes like this. X and y are both increasing close to 0. All right, and then let's take a look at this one. So here we have x being t squared, y being t cubed. For all real values of t. All right. Well, x equals t squared, y equals t cubed. This would mean that the cube root of y is equal to t. And then apparently if you square that, you get x. So x is going to be the cube root of y squared. And we have a notation for that. That is literally what we mean by 2y to the 2/3. Now this happens to be a curve that you might not immediately know how to graph, but that's fine. It looks something like this. A bit bizarre, but that is how it looks. And now as t increases from negative to positive, y is increasing from negative to positive, because t cubed has the same sign as t. So that means that this curve is being traversed this way. Goes up and continues to go up. All right, then we have x is e to the t, y is e to the negative 2t. And again, the range for t is all real values. In order to do this one, we have to recognize that x squared is e to the 2t, and that happens to be 1 over e to the negative 2t, which is just 1 over y. Ergo, y equals 1 over x squared. But again, we have to be careful, because in going from a parametric to a Cartesian description, we are losing some information. T is going over all real values, but no matter what t is, if t is a real value, then e to the t has to be positive. Okay? That means that this curve, which would normally have a wing on this side, is actually only going to have the part where x is positive. Okay. Then suppose we have x is root t plus 1, y is root t minus 1. Now to come up with a Cartesian description, all you have to do is say x squared is t plus 1, and y squared is t minus 1. Okay, so that means that if I take x squared minus 1, I get t, which happens to also be what I get when I take y squared plus 1. In that case, what we're dealing with here is x squared minus y squared equals 2. Now that, which again you may or may not have learned in pre-calculus, is a hyperbola. Okay? Hyperbola, just recall, is a curve that has two asymptotes that are perpendicular to each other. So for example, if you have two asymptotes that look like this, A hyperbola could be some shape that goes like that. And by the way, this might look similar to the graph of y equals 1 over x, just flipped on its side a bit. That it's supposed to. It's supposed to because y equals 1 over x is a hyperbola. It's just a certain one. Okay? Anyway, x squared minus y squared equals 2. Well, this has a solution for x when y is 0, namely plus or minus the square root of 2. So it's going to pass through plus or minus the square root of 2, which is approximately like right there, and approximately like right there. And then it's going to do the normal hyperbola thing. So we're going to have these kind of wings coming off of it like this. But again, that's not quite it. Because again, we're losing information when we change to this Cartesian description. In this graph right here, we could have that y is negative, x is negative, whatever. But in the parametric description, we see that x and y actually have to both be non-negative. So what we're getting here is actually just that. As x increases, or as t increases, x and y both increase, so the curve is traversed this way. Okay, let's do one more. So this one is going to be x of t equals 10, x of theta equals tangent squared theta, y of theta equals secant theta, and theta is between negative pi over 2 and pi over 2. You can do that, right? You don't have to call it t. It's just a name, right? It's not like math would somehow change if we decided on a different name for the parameter. So in this case, we're calling it theta. Fine. So to come up with a Cartesian description for this curve, again, you just have to find an equation that relates the two, x and y. So in this case, all we need to use is the fact that tangent squared theta plus 1 is secant squared theta. So x plus 1, well, that would be tangent squared theta plus 1, which happens to be secant squared theta, which is y squared in our case. This gives us x equals y squared minus 1, which is at least part of a parabola. Okay. Now let's see here. If we were to graph that parabola in its entirety, its axis of symmetry would be the x-axis. It would open upward along the x-axis. Its vertex would be at negative 1, 0. Would pass through the points 0, 1 and 0, negative 1. And you know, it'd do the normal parabola thing. Like this, except not all shaky. Right, so if we were just given this is what we would have. But we weren't. We were given this this parametric description. And specifically, we were told that theta cannot be less than or equal to negative pi over 2. It cannot be greater than or equal to pi over 2. So let's think about that for a second. If well, okay, first of all, no matter what theta is, x has to be non-negative because it's the square of some real number. All right, so that means that we are definitely not dealing with any region where x is negative, which would be to the left of the y-axis. Additionally, if theta is between negative pi over 2 and pi over 2, then the cosine of theta is positive. If the cosine of theta is positive, then the secant of theta, which is 1 over the cosine of theta, has to also be positive. So that means y is positive. So that means that we can only be dealing with this part of the curve. Now, the really weird and hard part about this is in what direction is this curve traversed? This one is really weird because, let's think about this for a second. If theta is between negative pi over 2 and 0, okay, it's between negative pi over 2 and 0, well, that would mean that the cosine, and therefore also the secant, would be positive and increasing. Wait, hang on. The cosine would be positive and increasing. The secant would be positive and decreasing. Okay? So that seems to indicate that we're moving down the y-axis, which would seem to indicate that we're moving like this direction, right? Well, if theta is between 0 and pi over 2, then the cosine is positive but decreasing, which means that the secant is positive and increasing, which means that y is increasing. So that would seem to indicate that we're going the other way. Now, what's going on here is this curve is being traversed twice. You see, as theta increases from negative pi over 2 up to 0, it comes all the way from infinity down to here, hits 0. When theta is 0, it just hits the y-axis. Then from 0 to pi over 2, it bounces off the y-axis and goes back in the opposite direction. So, what this illustrates is that sometimes it gets weird. Sometimes it gets weird because sometimes if you aren't smart about how you give a parametric description its bounds for the parameter, you might end up traversing the same curve more than once, possibly even in different directions, like in this case. Now, if you only wanted to traverse this curve once, and let's say from left to right, all you'd have to do here is to say theta can't be less than 0. If you do that, then suddenly this has to be just rightward. Okay? In any case, homework problems are pretty much like this. They're just going to ask you to sketch and or come up with a Cartesian description for a parametrically defined curve. Okay? So go ahead and get some practice with that.